let's see how this works. We said that for this original case, I equals RT. In this case, we had our R is equal to 10 t-shirts per hour, and we had a T is equal to 12 minutes equals 0.2 hour. So I equals 10 times 0.2 equals 2 t-shirts. And what did this mean? It's enough t-shirts to keep our bottleneck working all the time and achieve a flow time of 12 minutes, which is as good as we can do here. 3 minutes plus 3 minutes plus 6 minutes. Now, we change colors, pen here. Let's say we want to try to speed things up. Let's say we're going to do this by putting some more t-shirts into the system. For example, instead of 2 t-shirts, let's put in 3 t-shirts. For example, I have a t-shirt here at sew, call that t-shirt 1, a t-shirt here at cut, I'll call that t-shirt 2, and a t-shirt here at insert, I'll call that t-shirt 3. Now let's see what happens now. Now, first of all, don't forget, when a t-shirt is being processed here in insert for 3 minutes, there's no way it can move on. There's no place to hold inventory until the t-shirt at cut is finished, which is also 3 minutes. And it cannot move on until the t-shirt at sew is finished, which takes 6 minutes. So, if you have t-shirt 3 entering our system, now don't forget, this is not an empty system. An empty system, t-shirt 3 could just go straight through. There's a t-shirt at cut, t-shirt 2, and there's a t-shirt at sew, t-shirt 1. So, the t-shirt 3 enters the system and takes 3 minutes. The material gets 3 minutes to be inserted, and then it would like to move on. Well, it could move on because the t-shirt at cut also took 3 minutes, but the problem is the t-shirt at sew needs 6 minutes. So in other words, t-shirt 1 here is being sewn in 6 minutes. T-shirt 2 has to wait gets processed for 3 minutes to cut and then has to wait 3 minutes, which means t-shirt 3 also has to wait. So t-shirt 3 has to wait 3 minutes after it's inserted. And again, why? Just write it down to clarify. So 3 has to wait 3 minutes till 2 can move to sew. 2 has to wait 3 minutes till 1 has been sewn. That's clear there. All right. Once that happens, though, then 2 can move over to sew. The t-shirt 1 is done, and 3 can move over here to cut and gets cut for 3 minutes. But then the same thing happens. Has to wait 3 minutes. And why? 3 has to wait until 2 is sewn. And then finally, when t-shirt 3 finally moves into sew, has 6 minutes. And so in total, you have 3 plus 3 plus 3 plus 3 plus 6 is 18 minutes. It's your flow time. What happened here? Well, let's look at I equals RT. And let's write down T is equal to I divided by R. This time we put in 3 t-shirts into the system. Our rate didn't change. We're still processing at 10 t-shirts per hour. So we get here 0.3 hour times 60 minutes per hour equals 18 minutes. 18 minutes compared to 12 minutes. What does this mean? Well, Little's Law is still valid, of course. But if we have more inventory with our constant throughput rate given here by our bottleneck, then I equals RT. If you increase the I, R stays the same, the throughput time, the flow time has to increase. This means with more inventory, T-shirt 3 entering the system will take a longer time to finish the process. Very interesting, huh? Let's look at our skateboard example. Here our T was our flow time, was 5 plus 4 plus 6 minutes is equal to 15 minutes. That was our minimum time, a sum of all the different processing times. Our rates, now again, you can do this yourself, 1 over 6 minutes. This is the bottleneck, which is equal to 10 boards per hour. Same example as we did before. Now, what does this mean then? 15 minutes is 0.25 hour. I equals R times T is going to be 10 boards per hour times 0.25 hour is 2.5 boards. So this is our critical whip. This is the whip you need to keep paint working all the time. You need to have on average 2.5 systems, and if you have that, then you will also achieve this minimum flow time of 0.25 hours. Let's look at this also in a Gantt chart. So here's the chart again, and here we have paint working away all the time. 6-minute cycle here. And again, we're going to be using this idea of cycle time, the production cycle. Now, in this 6 minutes that paint needs to do its job, we're going to have a handover from sand every 6 minutes. Every 6 minutes, sand will have to finish a board and hand it over to paint. And for that to happen, every 6 minutes also, we're going to have assembly handing something over to sand so that it can then hand over to paint. So let me change my color again here. If we look at the production cycle here, and if we colored in a few more production cycles, what you notice is the pattern is always the same. You can actually shift this around, but in every single 6-minute block, again, the 6 minutes is given by our bottleneck at paint. You're going to see the same pattern repeating itself. And now, where did we get this information? Was I equals RT is equal to 10 times 0.25 was 2.5 boards in our system. Well, paint needs to always have a board, right? So you need to have a board sitting here at paint in every 6-minute cycle. Now, but you don't need to have a full board at assembly and sand. In the 6-minute cycle, assembly is only working, let me change color again here. Assembly is only working 5 minutes. 1, 2, 3, 4, 5 minutes. And sand is only working 1, 2, 3, 4 minutes of the cycle. All right, these are all the minutes, whereas we have the paint is working the full 6 minutes. So in assembly and sand, you're only working 9 minutes of the total 6 plus 6 or 12 minutes that they have available to them. So you don't need the full 3 boards in the system. In fact, you only need 1.5 boards in assembly and sand to paint's 1 board. So if we made a picture of that here, in assembly and sand, you're going to need 1.5 boards being processed, and here in paint you need 1 board, and that gives you the total of 2.5 boards, which comes directly out of the math that we've seen before. Now, what is interesting for us here is that we've achieved with this critical whip, we've achieved this minimum flow time that we can have with the process times given by assembly, sand, and paint. What is also interesting is if our R is fixed, if we increase that flow time, then the inventory is increased. Or likewise, if we increase the inventory, then the flow time is increased. And of course, this has not only a lot to do with lean, but just production control in general. So let's look at this the significance for lean production. So we already know that a factory manager would be interested in the speed of the process, what we're calling the flow time. We've also said we're very interested in the rate. How are the machines, which machine is our bottleneck? Which resource is our bottleneck? How fast can we produce parts per time period? And we talked about the process capacity and how the bottleneck capacity will give us a process capacity, assuming we have enough inputs and demand. Now we know that these are both related by inventory. Now let's look again at the 7 wastes. We have transportation, inventory, motion, waiting, overprocessing, overproduction, and defects. And already we see that inventory is clearly a problem. So, obviously, if we have additional transportation or motion, this goes into increasing our flow time, which we know for a constant bottleneck capacity will increase our inventory. So we have a waste here, which creates waste there. Additionally, we saw if we have too much inventory, we end up having some waiting around, which also increases our flow time, also shown by Little's Law. On the other side of things, overproduction and defects. Well, if you're producing too much, and yes, if you're producing too much and you can't sell it at the end, or it's building up at the end of the process, that's one thing, but overproduction within the process is the same as increasing your inventory in the process, which means something coming into the system will have to wait for the parts that are building up in the process to finish before it goes out, which increases the flow time. And defects also, that is also a part of inventory. You're wasting time producing parts that cannot be processed, that cannot be sold, again, causing the flow time to go up then for good parts. So I hope you see how important Little's Law is, and it's a very simple equation. It's a very simple relationship, but a very powerful relationship. And we'll be looking at it again.